In this video, we're going to learn about the sampling distribution of the sample mean. To understand the sampling distribution, first of all, we should have the concept of population. A population can be understood as a large group of target data from which we want to conduct a statistical study. For example, suppose we are interested in the distribution of the weights of the people in a city. Then, the population is the set of data of the weights of all the people in that city. Suppose now it is given that the population mean and standard deviation are 62 kg and 10 kg respectively. Usually, we use mu to denote the population mean and sigma to denote the population standard deviation. In fact, in reality, due to the large number of the data in the population, practically we cannot know all the weights in this population, and so we cannot exactly know the values of mu and sigma. However, it is possible to estimate the values of mu and sigma by selecting a subset of data from the population. And this subset of selected data is called a sample. Before we can understand how we should estimate mu and sigma, we need to firstly understand how the sample is related to the population in terms of probabilities. And this is going to be the main focus in this video. Now we let x kg be the weight of a randomly selected person from the population, and xi kg be the weight of the ith selected person. Then we know that the expectation of x is equal to 62 and the variance of x is equal to 10 squared. On the other hand, the number of data in the sample is called the sample size. For example, if now 20 persons are selected, then the sample size is 20. For the mean of the data in the sample, it is called the sample mean, and it is usually denoted by x bar. Unlike the population mean mu, which is a constant, the sample mean x bar is a random variable, and it can be larger than or smaller than the population mean mu due to randomness. Because x bar is a random variable, so it has a probability distribution, and we call this distribution the sampling distribution of the sample mean. In this video, it is assumed that we know exactly the values of the population mean and the population standard deviation. And we are going to analyze what the probability distribution of the sample mean x bar is. In the following calculations, we also assume that all the sample data are selected randomly and independently. Let's see what the expectation of x bar should be. According to the properties of expectations, we can take out the constant 1 over 20 and then expand it in this way. Because it is assumed that all the data are selected randomly from the same distribution, so each expectation here is simply equal to the expectation of x. As a result, we can get that the expectation of x bar is simply equal to the population mean mu. After that, let's take a look at what the variance of x bar should be. According to the properties of variances, we can take out the constant squared, which means 1 over 20 squared in this case. Then, because it is assumed that all the data are independently selected, we can expand the variance expression like this. Similarly, because all the random variables here follow the same population distribution, so each variance here is simply equal to the variance of x. As a result, we can get that the variance of x bar is equal to the population variance sigma squared over the sample size 20. Hence, we can get that the standard deviation of x bar is equal to sigma over square root of 20. In statistics, this standard deviation of the sample mean x bar is also known as the standard error of the population mean mu. In general, if the sample size is n, then the expectation of x bar is equal to mu, which is independent of n. And the variance of x bar is equal to sigma squared over n, which will be smaller if n is larger. Now we have obtained both the expectation of x bar and the variance of x bar. But we still do not know the probability distribution of this random variable x bar. And so we cannot even answer a simple probability question like this. Here we need to know two more theorems about the sampling distribution of X bar. The first theorem is that if the population is already known to be normally distributed, then the sample mean X bar is also normally distributed. However, if the population is not normally distributed, we know that the sample mean X bar can still follow a normal distribution approximately, given that the sample size n is sufficiently large. How large the sample size should be depends on how much the population distribution is deviated from the normal distribution. Empirically, a sample size of 30 or above can be regarded as being sufficiently large. This theorem is known as the central limit theorem in statistics. The central limit theorem is a very important theorem in statistics, as it confirms that no matter what the population distribution is, if the sample size n is just large enough, then we can accurately know the probability distribution of the sample mean X bar. The proofs of these two theorems are beyond the scope of this video, so let's just accept them as facts at this stage. Now let's take a look at 3 examples and see how we can handle problems related to sample means. In the first example, it is given that the mean and the variance of a population are 120 and 20 respectively. Then in part A, we need to find the expectation of X bar and the variance of X bar if the sample size is 5. For the expectation of X bar, we have learned that it is simply equal to the expectation of X. That means it is equal to the population mean mu, which is 120 in this example. For the variance of X bar, it is equal to the population variance sigma squared over the sample size n. Therefore, the variance of the sample mean is equal to 4. In part B, we need to find the minimum sample size n such that the variance of X bar is less than 2.4. In this case, we can simply consider that the population variance sigma squared over the sample size n is less than 2.4. Hence, we can conclude that the required minimum sample size is 9. Next, in example 2, it is given that the population follows a normal distribution with mean 7 and variance 20. Now, a sample of size 5 is drawn from the population, and we need to find the probability that X bar is between 6.3 and 11. From the population mean mu, the population variance sigma squared, and the sample size n, we can easily obtain the expectation and the variance of X bar like this. As X follows a normal distribution, we have learned that there is a theorem states that X bar also follows a normal distribution. Now we completely know the probability distribution of X bar, and so we can calculate the required probability. After standardization of the normal variable X bar, the required probability is equal to the probability that z is between minus 0.35 and 2. Hence, we can get that the answer is equal to 0.614. Finally, let's take a look at this example. In this example, it is given that the mean and the variance of the population are 40 and 33.28 respectively. Now a sample of size 52 is drawn, and we need to find the probability that X bar is greater than 41. Just like the previous examples, we can easily obtain the expectation of X bar and the variance of X bar like this. However, in this example, the distribution of the population is unknown, so we cannot know the sampling distribution of X bar exactly. But we can still estimate its probability distribution as a normal distribution by the central limit theorem. As a result, the required probability is approximately equal to the probability that z is greater than 1.25. Thus, the required approximate probability is 0.1056. This is how we can understand the sampling distribution of the sample mean.